continuing to look at the theory of classical mechanics. When I say system, I mean a collection of particles that we're studying. So in classical mechanics, also known as Newtonian mechanics, there's always way too many particles to study individually. Our objects are made of zillions of our systems containing zillions of particles. Too many to track them all individually. So we always have to make simplifying assumptions. We've got to simplify the system using some kind of model. And there are at least 3 different models that we can use within classical mechanics. So consider this scenario of a fellow throwing a water balloon. And let's look at 3 different ways to simplify that water balloon as we study its behavior. With increasing simplification going this way. So model 3 will be our simplest model. But starting with model 1, our balloon, we know it's full of water, and that water, well, that's comprised of zillions of little H2O molecules. And each H2O molecule is 2 hydrogen atoms and an oxygen atom. Each of those atoms contains electrons, protons, and neutrons. The first simplification that we can make, our model number 1, is to ignore the individual little atoms and electrons and protons in a molecule and treat the water as just a collection of molecules. Still zillions of them. So we want to look at the statistical behavior of zillions of molecules moving around, bouncing off of each other, rotating, vibrating back and forth. We can study that behavior of that group of molecules, and that branch of physics is called statistical mechanics and thermodynamics. Now, we can make a further simplification. Instead of looking at zillions of H2O molecules, we could take the water inside the balloon, this is going to be model number 2, and sort of divide it up into a grid, chop it up into little pieces, and we could call each one of those pieces a little fluid element. A fluid can mean a liquid or a gas. In this case, our fluid is a liquid, water. And we could cut up that liquid into a bunch of little pieces that are all next to each other. Millions of pieces, but still far fewer than molecules we have. Each one of these little fluid elements, I've colored in a few, contains zillions of molecules. One little fluid element contains zillions of molecules. But we have millions of fluid elements still here. So if we treat our system like this by dividing it up into tiny pieces, but pieces that are still much bigger than individual molecules, we call that model fluid mechanics. Or if this weren't a fluid, if it were a solid object and we divided it up into little tiny pieces like this and studied it one piece at a time, we would call that finite element analysis. This is a very common procedure in engineering. That's our second model. So we simplified it by, instead of looking at zillions of molecules, looking at just millions of little pieces. Here's model number 3. We're going to take our entire balloon and treat it as a single point. We're going to treat the whole balloon, all those zillions of molecules, as a single object, a single particle. We'll call it a point mass. And for lack of a better term, we could call this model just classical mechanics. This is the model that we're almost always going to use. We'll take a very complex system here and treat it as though it were a single particle. Now, where should that particle be located? Well, here's another complex system, a chicken. This real chicken is a system composed of zillions of atoms. We could simplify it using this model and treat this entire chicken as a single object. When we treat a system as a single point particle, we now call it an object. So this is a system, this is an object. It occupies a single point in space. We now are taking our real chicken and turn it into a point particle chicken. So where should this point be located? Is it like up here by the eyeball? Or is that point down here by the foot? It's going to be right around the middle of the chicken, which seems reasonable, at a spot that we call the center of mass of our chicken. The center of mass. It's the spot where if you were to hold the chicken up on your finger, you could balance the chicken right on that spot if you held it near its center of mass. So we're going to take our whole chicken and reduce it down to shrink it, compact it, so that all its mass is located in a single point here. All of it is going to be located in the center of mass, CM for short. Turn our chicken into a point particle. We turn our system into an object. That's model number 3. So this path here, we know that it's a parabolic path for our projectile. This parabolic path is actually the path of the center of mass of that balloon. Not every single molecule is following this exact path. You know, the little knot on the balloon is moving around and spinning in different places. It doesn't follow an exact parabolic path. But the center of mass of the balloon will be located on that parabolic path the whole time. So our point mass here, that is the center of mass of the balloon. In this model, when we treat this whole system as a single object with all its mass located at a single point, that point is the center of mass of the object.